Howdy folks, I like to make a prediction based on the theory that gravity is you can also express it. Of course the formulas of Einstein remain the same in the theory that I'm presenting you, that the quantum fluctuations make sure that particles, and I have just taken a movie of the parking place again, and I hope I can put it on. I missed the cable of my mobile phone. This is, by the way, my mobile phone, on which I've made so many YouTube films. This is the one. This is it. This is the mobile phone that I used for so many films. It's a very simple Nokia. It's effective. I made a lot of movies with it. But okay, I turn now to Movie Maker, which is fine. Which is better actually, but I missed the cable for it, so I just made a movie of the parking places here, close by here, to show you where the dirt is gathering, there where the quiet places are. But I like to make a prediction based on this. I'm telling in that movie, and I'm also telling it right now, that we experience gravity because of the quantum jittering of the quantum fluctuations of empty space. Which is a reality. The Casimir effect is based on it. But the quantum fluctuation actually also makes sure that chemical processes and all kinds of processes run in a certain kind of speed. And if you come closer to a big mass, then actually what happens is that the quantum jittering slows down, so that like in Brownian motion, but also with that's why I showed you the parking place gathering of dust and dirt. It gathers where the motion is the least, the least motion. And that's what gravity actually based on quantum mechanics is actually. And I like to make a prediction based on this idea. I mean, if you present a theory, it also must predict something. And I predict that closer to a big mass, that the Casimir effect is smaller. And that in open space, where there's more quantum jittering, that the Casimir effect is bigger, in the same ratio as that the time is passing slower to a big mass compared to outer space. So if the times passing, the time dilitation is a certain amount close to Earth, then the Casimir effect is related to that. The force that you can measure is related to the quantum jittering, the virtual particles. But if you go to open space, the Casimir effect must be bigger due to a more violent quantum jittering. So that's actually a prediction, and it's in the same ratio as the time dilatation due to gravity is in open space. There is less time dilatation in open space, and the ratio of the Casimir effect is related to that. I mean, if there is less jittering, then if there's less jittering here on Earth, there's little force. But if there is more quantum jittering, then the force must be bigger. So that's my prediction. So this theory can thus in this way be tested. That you send a probe outside with a Casimir to test the Casimir effect and see if it's in exactly the same ratio as the gravitational time dilatation is. This is, but that also means that due to this process, this idea, if I'm right, I mean, suppose I'm right, I may be wrong, of course, but I hope I'm right. But that also means that the Hawking's radiation close to black holes is zero, because the quantum fluctuation over there is far more less than in open space, because in my theory the quantum jittering, which acts like a Brownian motion type of phenomenon in making that real particles are jittering around. They never stand still. I mean, even if you go to zero temperature, it's always jittering around a little bit because due to this quantum jittering. So you can never, you cannot put silence a proton or a neutron or a quark or an electron. They will always jitter around because of this quantum fluctuation. But if I'm right and the quantum jittering is slower down or less, in lesser extent, close to a heavy body like an Earth, like a sun, but also like a black hole, then the quantum jittering and a heavy body acts then, if we live in a vibrant universe as I predict, as I think, then a heavy body acts like a node in a wave thing, in a wave where it's wavy. So a heavy body acts as a node, but that also means that the quantum jittering is less close to a heavy body, and that the Hawkins radiation, in which the virtual particles are separated due to the heavy gravitational field of a black hole, and they get separated. So, but then, if I'm right, if my theory is right, and there's less quantum jittering closer to a black hole, then the Hawkins radiation may be absent or very low, lower than maybe predicted. Well, this is my prediction. And not only that, but we experience, because this quantum jittering brings about all kinds of processes, chemical processes and so on and so on. And if they slow down, then also we experience time in a slower rate. If you go up in open space, then the quantum jittering is very much is higher, so processes take place, also chemical processes and so on take place more rapidly. So we experience time also more rapidly. This is the idea, this is the theory, and it must be able to be tested by the Casimir effect, that the Casimir effect is smaller here on Earth than in open space. If you have the same distance, then the force in open space will be bigger, and it's pressed harder to each other than here on Earth. And in the same ratio as the gravitational time dilatation is. So the passing of time here on Earth is slower than in open space, and this effect is in the same ratio as the gravitational time dilatation. And so you must be able to measure in the same ratio, if you go higher and higher and higher, then you must be able to measure a higher Casimir effect corresponding, linear corresponding with the time dilatation in open space. So you can calculate all that. There's some wonderful math about it. So it's already invented. And but this is my prediction, and this may also be a cause of where well, I'll come to that next time maybe. Okay, this was my first prediction of the theory I presented you a moment ago, in the other movies, and well, feel free to test it. Okay. Thanks for watching. Hasta la basta. See you next time. Bye bye.